Okay, Physics H. Let's talk a little bit about forces and force diagrams, all right? Something called object-agent notation. All right, object-agent notation. So, let's just look at a really basic force, right? Let's say we've got a box sitting on a table, right? Or sitting on the ground, and we're gonna push that box. So generic stick figure of physics. We're gonna push that box. So we're gonna look at that force of the push, force of the person on the box. So this is a box. This is a person. Box and a person. So when we make a force diagram, right, we're going to draw the forces acting on the object. All right. A force diagram, you actually show the force acting on the object. A free body diagram is something a little bit different, which we'll talk about in a second. So let's say here's our box now. Okay, let me move this up a little bit. Here's our box. I'm not going to draw the ground. I'm just going to look at the box itself. All right. Well, the force of the person we represent with an arrow. Okay. And we give it a name, and we call it the force of the person on the box. Force of the person on the box. All right. The object is the box. The agent is the person. So when we label forces acting on something, initially we're going to write this out, right? We're going to write a capital F for the force, and it's going to be of the agent on the object. Force of the agent on the object. Now, the agent, there could be different agents here. For instance, the box has more forces acting on it. All right. It has actually, Earth's gravity is trying to pull it down, right? The Earth is literally applying a force to pull the box down. And if I was to zoom out and draw the Earth, you know, there's the Earth and here's the box, let's say, right? The Earth is literally pulling the box towards the center of the Earth. So this is the force of gravity, which I'm going to draw acting on the center of the box. But I'm not going to call it the force of gravity. I'm going to call it the force of the Earth on the box. So the object is always going to be, you can think about these like filling in the blank, right? F of blank on blank, right? So you can fill in the blanks there. So the box is the object, the Earth is pulling it down. Well, what's preventing it from falling down? Well, the ground, right? The ground is holding it up. There's actually another force acting on the bottom of the box to hold it up, which is, I guess it's technically the Earth as well. I mean, let's just call it the ground, though. So this one, a little bit hard to see because I wrote the word box in there. The ground supporting it, you can see why we start writing this differently, right? It's actually quite a pain to draw these forces as if they're literally acting on the object. Now, there's actually another force here holding this back, force of the ground and box holding up. There could be friction acting at this surface, which we'll talk about later on. I'm going to pretend it's frictionless for now. But something's preventing this. Maybe this box is not sliding, right? So there's a force of friction between the two surfaces here, and that friction is holding it back, right? It's actually pulling it back this way. Maybe I will just, it's a frictional force. But what is the object? What is the agent that's providing that frictional force? It's the ground. It's also, we have two components of the ground. Force of the ground on a box. So we end up with actually the ground holding it up and preventing it from sliding. Now, this is terrible to look at, right? So this is what's called a force diagram. All right, so force diagram, you draw the forces acting on the object and their literal points of application. So where the force is actually being applied to the object. So, you know, we draw it like that. Now, there's something called a free body diagram that's a little bit different. So let me keep this over here for a second, and let me convert this to a free body diagram. Actually, I'll just fold this in half. I'll fold it over so we can still see this crazy drawing. All these crazy drawings, right? A free body diagram is a little bit different. Rather than drawing the object, we just draw a dot. We call that a free body. That dot represents the object. So the object, is still the box, and this dot is representing the box. What this does is now when we draw the forces on it, we start the force arrows on the dot. So this is the force of the person on box. Then we have the force of the earth pulling the box down. So it's the force of the earth on box. Now I'm still doing the long notation here. And then we're going to have force of the ground on the box. All right, and that's the horizontal component. And then we're going to have the vertical component of the force of ground on the box as well. All right, and that's a much nicer way to draw this, right? We can see that the forces are balanced, right? So this is called a free body diagram. And I've run out of space here, sorry about that. It's a free body diagram. So it's a much nicer way to draw these things. It is worthwhile initially, though, to really kind of look at where are these forces literally being applied to the object, right? And it looks kind of messy. Gravity, Earth always acts on the center of mass of the object. These contact forces always act on surfaces of the object, right? And all of our forces here are going to be on the box. The dot is the thing the forces are acting on, right? So if the forces are balanced, this thing's not going to move, or it's going to move at a constant velocity. That's Newton's first law, right? And we'll talk about that more in class, but Newton's first law says an object in motion will stay in motion unless acted on by an outside force. Well, also, it'll stay at rest if not acted on by an outside force. But you might say, okay, there's a lot of forces acting on this. Well, there sure are, but they're balanced. So it's probably a better thing to say an object will stay at rest or in constant velocity motion as long as the forces are all balanced. Okay, that kind of covers everything. If the forces are all balanced, the object will stay in the state it is in, meaning it'll stay moving at a constant velocity or it'll stay at rest. At rest is a constant velocity, right? The velocity is 0 meters per second. So that's Newton's first law. That's a pretty important one. So that's just a basic quick introduction on how to draw force diagrams and free body diagrams, all right? And we're going to apply that to worksheet 1. All right, so that's it for now. I'll talk to you later.